Maths educational video. In this video, we will learn the method of computing the so-called radius of convergence of a power series. Here's a quick summary of all the three cases that we have learned in the previous video. Our job is to compute R. It turns out that the method we need is the so-called ratio or root test for power series. Here's the outline of the method. First, we let AK be the sequence that we are summing. If you choose to use the ratio test, you will calculate this quantity, which is the limit of the ratio of AK plus 1 to AK with the absolute value sign. Let this be equal to L. If L is strictly smaller than 1, the power series converges. If L is strictly greater than 1, the power series diverges. If you choose to use the root test, you will compute another quantity, which is the limit of the kth root of AK with the absolute value sign. And the same conclusion will follow. I'm going to show you three examples to cover all the three cases. In example A, we are asked to find the radius of convergence of this particular series. Let's try to use the root test. You should get the same conclusion if you use the ratio test. We begin by defining AK to be the term that we are summing. We take the kth root of AK and take absolute value sign. Applying the indices law, we will take the kth root on each and every term, 3x minus 2 power k, k and 4 power k. That will lead us to this term, and we're going to take limit k going to infinity on this particular term. But as you can see, the only term involving k is this guy. So all we have to do is to take limit on k to the power of 1 over k. But we have a result that says k power 1 over k will converge to 1 when k goes to infinity. So the resulting limit is given by this quantity, and we let it be equal to capital letter L. Following the conclusion of the root test, we can now conclude that the series converges if L is strictly smaller than 1, meaning this quantity is smaller than 1. But in order to find the radius of convergence, we have to write this inequality in the form that you will see in the red box. So obviously you have to multiply both sides by 4 over 3 so that you get x. The coefficient of x has to be 1. So the conclusion is the radius of convergence is 4 over 3 for this particular power series. Let's look at example B. This time we use the ratio test. And the reason is obvious. The presence of this term, k factorial, tells us that the ratio test is a more sensible choice. So that's the rule of thumb. Whenever there is a factorial term, the ratio test is preferred to the root test. So following the ratio test, we are going to compute the limit of this quantity, the absolute value of AK plus 1 divided by AK. Let's simplify this expression. We are going to use a famous result to this term. K plus 1 factorial is equal to k plus 1 multiplied by k factorial. So if you apply this result, this ratio can be reduced to k plus 1. And it's this term that we're going to take limit on. We're going to let k go to infinity. Obviously, when k goes to infinity, so does k plus 1. So therefore, the limit is equal to infinity, which is obviously greater than 1. So we conclude that the series diverges for all x, and not to forget, except when x equals to the center of the series. In this case, that's when this term in modular sign is equal to 0. So this is only exception. So anyway, this is case 1 when the radius of convergence is 0. The last example is to cover case 2 when the radius of convergence is infinity. This time we apply the root test again because there's no factorial term. We take the kth root and simplify, and we let k go to infinity. Obviously, k power half will go to infinity. But this term appears in the denominator, so the resulting limit is 0, which is smaller than 1. So we conclude that the series converges for all x, and hence r equals to infinity.